Today's video we'll be looking at heat transfer by radiation. So now when we say radiation, it's a mode of heat transfer from a surface to another surface or a space where vacuum exists. So mostly we associate that with a black body. So sometimes we hear black body radiation and stuff. So now with the radiation, it's a mode of heat transfer from a surface to any other space or to even another surface whenever a vacuum exists. So now to solve problems under radiation of heat transfer, the equation we used mostly is using the Stefan Boltzmann law, which states that your Q is equal to sigma A T1 exponent 4 minus T2 exponent 4. Now, so this is the equation we're using to solve radiation problems. So now we have a body. So let's say body A, and then it's emitting heat to another body B. Right? So let's say body A emits heat, right? So it emits heat. There is heat emitted around the body. So some gets attached to B, and then some moves to the atmosphere. So now when you want to find the heat transfer from A to B, in which we are considering only the heat transfer by radiation, then we can say that all the heat emitted by body A is being absorbed by body B. So therefore, we have a factor we call the VU factor or the geometric factor. So the geometric factor is represented by Fg. So then we correct that and say our Q is equal to Fg sigma A T1 exponent 4 minus T2 exponent 4. And then as compared to this, then so now our heat transfer rate or radiation becomes F E multiplying Fg sigma A T1 exponent 4 minus T2. Fg is our geometric function. Our sigma here is our Stefan Boltzmann constant, which is 5.67 times 10 to the power -8. And then our A here is our area, so our surface area we're looking at. Our T1 is our hotter temperature and our T2 is our colder temperature. So when you want to solve any problem under heat transfer by radiation, this is the formula you're going to use. So now we can have modifications to this formula, modifications to the formula. So in the sense that whenever the emissivity is 1, so let's say when you are considering black bodies, we know that sigma A T1 exponent 4 minus T2 exponent 4. So this is it. So now when you are considering two bodies A and then body B, right? So now and then A emits heat by radiation to body B. So it emits. Now we can see that body B engulfs the whole of body A. So all the heat emitted by body A is being absorbed by body B. So we can see that the view factor or the geometric factor for this problem becomes Ft is equal to 1 because now everything emitted by body A is being absorbed by body B. So now our Fg also becomes 1 and then we are left it sigma multiplying A T1 exponent 4 minus T2 exponent 4. So now these are the modifications. So now when you are dealing with black bodies, there is no Fe because it's 1. And then when the question says that body A engulfs body B, then it means that our Fg is also 1. and then both FE and then FG becomes 1. We are left with sigma A T1 exponent 4 minus T2 exponent 4. So let's solve the question. Now the question says that two infinite black plates. So the moment you hear black plate, then we are dealing with black bodies. Right? So now the resistivity is 1. So Fe is equal to 1. At 800 degrees Celsius and 200 degrees Celsius, exchange heat by radiation. Calculate the heat transfer per unit area. So the moment you realize that we are dealing with radiation, then we can see that our Q is equal to Fe Fg sigma A T1 exponent 4 minus T2 exponent 4. Now, for black bodies, our Fe is 1. So that one is out. Now, let's come to our Fg. We are dealing with two infinite black plates. So the moment we say infinite, that means our view factor is also 1. So our Q becomes sigma A T1 exponent 4 minus T2 exponent 4. But then we have no information on the area, right? We can just divide through by area. And then we get Q over A, which is our heat transfer per unit area, equals sigma T1 exponent 4 minus T2 exponent 4. And then one thing you should also take note is that for the Stefan Boltzmann law, our temperatures are supposed to be in Kelvin. So T1 is 800. We convert it into Kelvin, 270. This is because they are both raised to the power 4. Supposing it was just T1 minus T2, then using Kelvin or degree Celsius would have yielded the same answer. But then it's to the power 4 to the power 4. So we have to convert into the actual SI unit. And then this gives us 1073 Kelvin. And then T2 will give us 200 plus 273, 473 Kelvin. So now we just substitute Q over A equals Stefan Boltzmann constant is 5.67 times 10 to the power negative 8 multiplying 1073 exponent 4 minus 473 exponent 4. Now you get Q out of A to be equal to, once that so we get 72321.07 watts per meter square. Now you can convert it into kilowatts and say our answer would be 72.321 kilowatts per meter squared.